Everybody, what's going on? And welcome back to another episode in our Back to Basics. What we're going to be doing today, or technically at this point it's this evening, but whatever. What we're going to be doing is we're going to be talking about transistors, and we're going to talk about both major types. There's actually a barrage of flavors out there. There's tons of, from everything from JFETs to, I think there's even an SFET or something like that. And I can't remember, there's like a zillion different kinds out there. What we're going to be talking about are the main two that you see everywhere. And they're going to be the BJT, the Bipolar Junction Transistor, and the Mosfet was what we'll be talking about. And right now, we're going to talk about this brand, the Bipolar Junction Transistor, or the BJT. Often you hear these referred to as just transistors because most of the time everybody thinks of Mosfets when they're thinking of different types of logic or digital control systems. They're thinking of Mosfets. But BJTs have their place. BJTs are mostly the oldest of the two. Mosfets are fairly new, not like, really new, but, since a long time. It's been quite a while. It's been like, how old are Mosfets? I'm going to get ahead of myself here. I don't know. I think we started doing that maybe in the 60s or something. I think 60s, somewhere around in the 60s, I think was when Mosfets started becoming really popular. Before that, it was all, the BJTs. So the transistor radio, that was a BJT. But what we're going to be looking at is we're going to be looking at the digital side of things, basically on and off. We're not going to be messing with any signal processing because this is a basics course. So what we'll be looking at is how these guys can be used in what's called the cutoff or off mode and the on mode or the saturation region. There is a region in between, just like everything else. It's called the active region, and that's where basically it's not totally on, but yet it's not totally off either. And we're not going to play with that for right now. We're just going to look at the on-off characteristic of them, which is called the cutoff region or the saturation region. So anyway, there are two different types generally. There's the NPN and the PNP. Now, if you remember right, how a diode was, remember it was two different types of material. If you looked at the last video, which I encourage you to watch, the one on LEDs, I talked a little bit about diodes and how they're made. There are basically two different types of material that are put together, a positive type and a negative type. Well, with a BJT, there's actually three components to that. We're looking at the N type. We're going to look at, and we're going to just call them a low side switch. The P type we're going to call the high side switch, okay, for all intensive purposes. I mean, like I said, there's a whole world of stuff that's for signal processing where you actually use these as amplifiers and things like that. We're not going to be doing that. We're just going to be looking at them as a solid state switch, okay? So basically, for a high side switch, what we're going to have is, let me get rid of some stuff here. We'll get rid of this picture for now. For a high side switch, what I mean by that is, say we got 5 volts here, we got some R, okay, and then we have some switch here, okay, and your output is here. So basically, right now with the switch open, my output is 5 volts, okay. Wow, this is hard to draw with these styluses. I don't know, does anybody have these problems with these styluses that come out for the iPad, these capacitive things? They're so squishy and they're big and, I don't know, they're just interesting to draw with. Okay, rant all to the side. Okay, so it's 5 volts right now because of this resistor pulling it up. If I close in this switch, that will then pull the current straight down, and this will change. Instead of being 5 volts, this will now be 0 volts. Okay? So that is basically a low side switch. I'm sorry, I think I said high side switch is what I was demonstrating first. This is the low side switch. I apologize. We're switching the ground. We're either making or breaking the ground. Now, in some situations, that's perfectly fine. That's perfectly acceptable. Other situations, due to let's say if you have different grounds separated by different values or something like that, it might not be good to switch the ground. You know, switching the ground could cause you to lift a ground in parts of the circuit that you don't want lifted, and it could cause, you know, potential differences that could cause current to run backwards and weird stuff like that. So there's situations where you want to use a high side switch. And so for that one, let's get rid of get rid of this. A high side switch is just the opposite. You're going to have the switch on the top and the resistor is going to be on the bottom. And of course your Vout in between. Say this is 5 volts. Okay. So how this is going to work is same difference. Right now, initially, it is 0 volts. Okay. Excuse me. I throw the switch in and it becomes 5 volts. Okay? So, whoa, it looks like a Y. It becomes 5Y. No, it doesn't become 5Y. It becomes 5 volts. Okay, more or less, you get the idea. So basically, they're inverses of each other. Okay? With the low side switch, initially, it's at 5 volts until you turn it on, and then it's at 0 volts. The reverse of that is a high side switch is always off. You know, you have 0 volts in the output until you throw the switch in and it pulls it then to the high, becomes on, 5 volts. Okay? So that's basically the two different types that we have to deal with. So I'm going to go ahead and clear us out here. Now, some simple equations, I guess we want to get equation-y, that you want to always remember. Is a good one is for the active region, for the cutoff region, basically everything's 0. So what we're going to look at is we're going to look at a simple NPN transistor, okay, model here. Now I'm going to show you why this resistor's here in just a minute. Call this R2. Good grief, it's hard to draw with this thing. Say this is 5 volts. All right, whatever. So this is basically our typical low side switch. This is an NPN BJT. Okay. Now the thing to remember with these, the main difference between BJTs and Mosfets is that a bipolar junction transistor, or, you know, like I say, a transistor, I'll probably refer to them as just transistors, they turn on with current. Yes, voltage plays a factor because you have to have a certain voltage to get a certain amount of current to pass, but they turn on with current. You push current from the base to the emitter. And oh, I better label the parts of it. I forgot to do that. Okay. I apologize. Let's back up for just a second. With a transistor, you have the base, the collector, and the emitter is what these are all called, these different points. Okay, the emitter, you always can tell the emitter because it's the one that has the arrow. And on a P channel or a NPN or a PNP, I think it should be backwards. Okay, let me draw this. Oh, this is hard to draw, this thing. The arrow is up top because it's basically the inverse, right? I said it's basically the opposite. Okay, so it's emitter, collector, but the base is still over here. Okay, this is PNP, this is NPN. Okay, so hope you're with me so far. So there's the two different types, and there's and so here's our example. So I'm going to go ahead and get rid of this. If you want to pause and write this down, go for it, or you know, you can always watch this video again. So okay, so we've got our kind of little sample circuit here. So now what's gonna happen is, like I said, it always turns on. We've got our base, collector, emitter. These turn on with current. And how they work, the model for them, which if you want to look at it, is the saturation model, is what we call it. You've got, let's say we want to turn this guy on. Okay, let's clear this out real quick just for a second. Move that out of the way. We're going to pull this to 5 volts, let's say. Okay, this is our base. What this looks like, the actual, like you would say, circuit model looks like, is you're going to have 5 volts. Boy, this is going to be interesting. We have this resistor R1, okay, for the base. And it basically, oops, I get this out of the way. There's going to be basically a little voltage potential here. Okay. As well as there's another one at the other side. Okay. 5 volts. This is the R2. Okay. Okay. So this is what it looks like. There's the emitter. This side is the collector. And this side is the base. Generally, you have a base, let's see, base to emitter and collector to emitter saturation voltage potential. Normally, the base to emitter voltage is 0.7 volts. And now I know what you're thinking. Hey, that's kind of like a diode. That's generally like a diode. It's exactly like a diode. Due to their construction, they're constructed similar, not exactly, but similar to how a diode is. There is a barrier voltage, okay? And I'll show you that here in just a second. Then on the other side, there's usually a collector to emitter voltage. And that is usually around 0.2 volts, roughly. Where these come from is exactly the same thing as like a diode explained in the last video. They are from a barrier voltage. Very, very simply, how these are put together is if this is an NPN, you've got a negative type material, a positive type material, and a negative type material. Okay? You have a collector, an emitter, and the base. Okay? Well, therefore, you're going to have a depletion region here and another depletion region there. Okay? That sets up these two voltages, the 0.7 and the 0.2. These two voltages, like a diode, which is just an N and a P type material put together, this is a diode. You only have one, you have that 0.7 barrier voltage you have to get rid of. You actually have two with this one since there's 3 different pieces of stuff put together. So you have to overcome both of these to be able to push current. So therefore, your voltage up here, basically in respect to the emitter, since we've grounded the emitter, I'm going to say this, the voltage up here, this one has to be greater than 0.7 volts for current to flow. Okay? Similarly, whatever voltage you connect your collector to has to be greater than this barrier voltage here for current to flow through the collector to the emitter. So again, BJTs are all done by current. Everything to do with them is done by current. Okay? So in order to turn these on, you need certain currents to do this. Okay, so now I'm going to go ahead and I'm going to get me some more space back. And I know this movie's getting kind of long. It looks like we're going to be putting this in two different videos. So we'll do Mosfets in the next video. But what you have to remember is that let's see. Well, if I can get this thing to right again. Okay, your collector current in your collector is equal to a beta, which I'll explain what it is in a minute, times your current in your base. That is a very simple but yet very useful equation. What your beta is your beta is your DC current gain. And when I looked at a data sheet, which we'll look at here in a minute, I tore that thing up trying to find this. I was like, where's beta? Where's beta? Where is beta? Beta is your DC current gain, or in a data sheet, they denote it by H which is the DC current gain. Okay? So now, alright, so now what I'm going to do is we're going to check out one of the data sheets on one of these. So I'm going to see if I can't bring this up. There we go. Okay. So the one that I've chosen is just a simple generic one, like it says, general purpose, just an N channel, an NPN. So we're going to look at the 2N3904. That's what we're going to look at today. So we look down through here, we've got the collector emitter voltage, which that tells you what kind of voltage it can withstand. Collector to emitter, it's got the collector to base voltage, also has the emitter base voltage that you have on there, threshold, absolute maximum. It also has the collector current, that's the maximum current that it can take. This one is only 200 milliamps. And then of course it's got your operating junction temperatures and all that fun stuff, power dissipation, all those fun factors. But I wanted to kind of direct you to a couple of different spots. Remember how we were talking about the beta in that equation, that your IC equals your beta IB? What we're going to be looking at is the HFE is actually your DC current gain. That is your beta. I looked for a long time when I was, so that's why it's showing you that at different collector currents here, you got some different minimum values. It's somewhere, anywhere from 40, 30 to 100. And then its maximum is 300 is the maximum current gain that you can get out of this one. And then I wanted to show you right here this VCE, collector emitter saturation voltage, and emitter base saturation voltage. Remember when we were talking about the two different voltage levels you have? Well, there they are. So it's showing you, and see, we've got around 0.2, 0.6 to 0.85, 0.95, somewhere around in there. But see, it's around 0.2 and 0.7. That's why those are just good generic. If you're just wanting to, on a general basis, get yourself in the ballpark, 0.2 and 0.7 is about what you need for the 0.2 is for the collector emitter saturation, and the base to emitter saturation use about 0.7. So it's about 0.7 of a volt different. I'm sitting here trying to look through. I made a note somewhere, and I am trying to find it, and I can't seem to find it. Oh well. Anyway, I'll look it up later. Anyway, I wanted to show you that, as well as, let's see, is there any other? Right, there's all these graphs too, and what these graphs will be telling you is like here's your collector current versus your HFE or your beta. And so that's showing you at different temperatures what your beta is going to do, and at different, not temperatures, at temperatures, sorry, it has temperatures on there. There's a couple, let's see, 3 different ones. There's -40, 25, and 125. 25 degrees is standard room temperature, and it shows you with the current that you're pushing through it, the collector current, it's going to show you what your gain will do. Now, this says pulsed current gain, so that means they're doing this as like they're pulsing it. They're basically hitting it for a few, I think it's milliseconds is what they do. I don't remember the exact test, but they do it for a few, either milliseconds or maybe 1 second or something like that, pulse of the current, and then that's how they get this curve. So anyway, that's what a lot of those curves will tell you, is different parameters, different things. If you want to see over a whole range of currents or voltages or whatever, they'll show you what those are. But basically, that's the different points that you need to look at on a data sheet that give you an idea of what kind of a beta you've got, or DC current gain, and then what kind of saturation voltages that you have, and also your breakdowns and your limits of your device. So I'm going to go back to our little pin thing. So how we turn these on is basically with current. Like I said, you're going to push current through the base to the emitter, and that will turn it on. Now, how you determine how hard on it is by that simple little equation that I showed you. That was our IC equals our beta IB. Now for that transistor, it seems that, well, generally it was anywhere, you could be from 100 to 300 depending on what you're doing. So let me see if we can't take a peek back at that. Where's it at? Here we go. So depending on how many milliamps you're going to push through it, it can be anywhere from 30 to 300. So what I would choose is probably like a good middle of the road, probably the 100. It's probably close enough. And so essentially what you would do, and I don't know, I have just a lot of from experience. If you want to turn it on, you know, hard on, a few milliamps is good to go. But if you want to actually calculate it, you can use this little formula here. So if you want a collector current of, let's say 100 milliamps, let's say, then what we'll do is we would say we have 100 millis is equal to, and then of course it's 100 times our IB, let's say. So of course you divide your 100 out, right? And that cancels, and it gives you 1 milliamp is your base. Oh my lord, that looks like an R. Doggone stylus is a swear. Anyway, so about 1 milliamp of current will give you about 100 milliamps through the collector. So that's how far on you will turn it. So that's basically kind of how you got to gauge these things. I would say, you know, and so that therefore, if we're still using our 100, which is our middle of the road value, which is good value for that guy, looks like a, you know, decent currents. It's basically that. You can put, you know, let's say 2 milliamps through it and get the full 200 milliamps collector to emitter. So, but let's say that we just want 100 milliamps, so we'll do that. So we need 1 milliamp through the base. So therefore, for us, let's get rid of. See if I can get rid of all this. Oh, go away, go away, go away. Okay, so 100 milliamps is what we're looking for our. Good grief, this thing. Okay, I base. So 100 milliamps. Sorry, guys. Still trying to draw with one of these styluses, and these things are interesting, especially if you're trying to move quick. 100 milliamps equals our IB. Okay, so essentially what we got to do then, if we're connecting our base to 5 volts here, then we're going to do our simple, just our normal V equals IR. Oops, that's a, no, it looks like TR. V equals IR. You know, essentially, we want 100 milliamps. We know our current, we know our voltage, we just got to find the R. So we've got 5 volts, we got 100 milliamps, so then there's the R that we need to do. So if we're at 100 milliamps, so that means, let's see, 100 milliamps is minus, about, what, 50 ohms, I think. That's what your R is going to equal. So you need about a 50 ohm resistor in there, in line. This R1 is going to be about a 50 ohm resistor. So there you go. So that's essentially how you do it. And that's why if you want to turn this around and use, let's say, an N channel, you can do current limiting with these guys. And these guys work wonderfully for current limiting because based on this base current, it links how much collector current you can push through. So you'll see things like, here, let me get a new page. I'll show you what I'm talking about. Let's say you've got some voltage source. I'm going to put a, you know, we'll go like this. You have some voltage source. You can actually take a P channel, okay, that's here. Let's say this is going like this, okay, and you've got some load here. This is some load, and we'll put RL, otherwise it looks like an inductor. RL. You got some load here. Well, if you take and you connect and you push, you know, you push some sort of current through via an external controller or something like that, you push some current through here, what's going to happen is you can actually control the current through here because IC is equal to the beta IB. So you're actually going to be able to control the current in this guy. Okay, so that's essentially how they do that, and how they use current controlling. Now the only thing you have to watch with it is the power dissipation of it. Okay, so that's where you got to watch what kind of voltage that you've got out here as well as what kind of current you're pushing through, because remember V times I is, is P, is your power. So back to the data sheet, that's when then you have to worry. Let's go back up here. Where's that? Oh, it's right here. Okay. Total device dissipation. Derate above 25 degrees, which means you gotta derate it, which means you gotta lower it. If you're above 25 degrees, obviously it's going to be less, and that's where you get the milliwatts per degree C, and you do that kind of thing. But if we're looking at the 394, this can handle 625 milliwatts. Okay, milliwatts. All right, can handle 625 milliwatts at 25 degrees ambient. Okay, so as long as you stay within a dissipation of 625, then you're good to go. So as long as you don't have, and like I said again, take the voltage across collector to emitter times your, at least that's a good rough estimate. I mean, you could get into trying to find the different resistances and whatnot that it has. You can figure that all out, but I mean, just a good rule of thumb to work by is just do a normal power calculation. Just do voltage across it, times the current you got through it, and whatever the power is, you got to be watch out and make sure that you're within that, in that range, within that 625 milliwatt range. And that's basically all you got to do. So essentially, these guys are current controlled switches is what they are. The voltage matters due to power dissipation, like I said, but it doesn't. It's not as significant as the current because of that. Our equation, our IC equals beta IB. That's the main. There's a few more equations that go with this, but you start getting into a lot of the whatever they are, the small signal models and things like that, when you start dealing with using these as amplifiers, stuff like that, which, like I said, we're not going to look at for this one. So I guess for looking at DC, one of the main ones you need is this one, this IC equals beta IB. That's the main thing you're going to be playing with, and so that'll get you in the ballpark of what you need to do to size your resistor here, as well as size your resistor here, or whatever load, whatever load that you got going on that you're syncing through this thing. If it be an N channel that you're syncing through it to ground, then an NPN, and then that'll be the one. But that's the main equation you want to use, and you can vary your base current to get different collector currents. Okay, and so that's how you do that, and they're linked through that DC current gain, and that's why it's called DC current gains, because essentially whatever you put through, it gains it essentially. So hopefully that wasn't horribly confusing, but that's kind of one of the quickest ways I can explain it without going into huge amounts of detail and taking 30 videos to explain everything. That's kind of the quick and dirty of it. If you have any other questions or anything, please let me know. I know I went through it fairly quick. Of course, I mean, this video is going to be pretty long, but honestly, I did go through it pretty quick, so there's a lot to them. But I tried to just hit just the DC side of things and how you can use one of these as a switch. The only thing, like I said, that's a problem is that if you're using lots of these, they're current hogs. Like I said, like we just calculated this one, that we almost need what was it? We need, was it a milliamp? Well, actually, this was a C. Sorry, I wrote IB. That needs to be a C. But what the base current was like a milliamp, right? Well, let's say you got a whole port full of these. You got 7 of them. You got 7 milliamps right there. Then you maybe have some other stuff that you're dealing with and whatever. So you start racking up the milliamps, right? And then maybe you're not doing 1 milliamp. Maybe you're pushing 5 milliamps on one of them or something like that, because you're really needing a lot of current coming through it. This one's a fairly small one, but let's say you got a big beefy one. It needs like 5 or 10 milliamps, and you got 7 of them. You got 70 milliamps on one port. The port on a PIC microcontroller is only good for 90. So that's what I mean. They're kind of current hogs. So you got to watch out and make sure you look at your microcontroller to see how much current it can source, because these guys are a current sink hugely, and so you got to make sure you can source enough current to turn them on and off. Now, having said that, that's why in the next video we'll be looking at Mosfets, which are a different, completely different construction, totally different type of device. That those are mainly voltage driven. They draw very, very tiny current on their gate, which the gate of a MOSFET is analogous to the base of a transistor, or of a BJT is what we're looking at. These are bipolar junction transistors. And so they're analogous. You know, you still turn it on with a base, instead of base to emitter, you're doing gate to source voltage. So they're voltage driven, these are current driven, and we'll see that in the next video. I'll show you what the difference is when we get to MOSFETs and how that they work as a DC switch, and they're not current hogs, and so you can gang up a whole ton of those on a microcontroller without having to make sure you have a huge amount of source current to be able to power them all. So okay guys, hopefully that clears up some of the confusion on bipolar junction transistors, or like the industry calls it, just transistors. Hopefully that clears up some of the confusion. If you need any more help, please let me know. Send me a email or PM or whatever, or drop me a comment below, and I'll try to answer it best I can. So anyway, that's pretty much it. And so like, comment, subscribe, share, all that fun stuff. And I guess I'll see you guys in the next video. And I guess with all that ought to do it. Take care, guys.